Okay, so most of us probably had to memorize the geometric series formula back in math class, right? But did you ever stop and ask why it actually works? Well, in this explainer, we're going to go way beyond just memorizing. We're going to uncover the beautiful and honestly super clever logic behind this powerful formula. And it all starts with this question that, let's be honest, feels like a total paradox. I mean, how can you keep adding numbers together forever and somehow land on a single finite answer? It just sounds impossible. But that is the big mystery we're going to crack today. All right, let's dive right in. We're going to treat this whole thing like a little math detective story. Our mission? Uncover the secret behind one of the most elegant formulas out there. First things first, let's just make sure we're on the same page. What even is a geometric series? It's basically a sum of numbers where, to get the next number, you just multiply the last one by the same constant value over and over. We call that the common ratio. You can see a classic example here. 1 plus a half plus a quarter plus an eighth. See the pattern? You're just multiplying by 1/2 every single time. Okay, so that brings us to the formula itself. You can kind of think of it like a piece of code that we need to decipher to really understand what makes it tick. And here it is. This is the formula for the sum of a finite series. So the S sub n just means the sum of the first n terms. The a is just your starting number, the very first term. And r, well, that's our common ratio we just mentioned. But the big question is, where in the world does this thing come from? It looks like it just fell out of the sky. Okay, this is where the magic really happens. The entire proof, the whole reason this formula works, comes down to one simple but totally brilliant algebraic trick. Seriously, this is the key move that unlocks everything. And here's our game plan for the big reveal. We're just going to walk through these 4 steps together. And trust me, it's way more straightforward than you might think. Okay, step 1, let's just write out what our sum, S sub n, actually is. It's the first term, a, plus the next term, which is a times r, plus the next one, a times r squared, and you just keep going like that all the way to the end. So far, so good. Now for that trick I was talking about, we take that whole equation we just wrote out and we multiply every single part of it by r. So S sub n becomes r times S sub n. A becomes RA. RA becomes RA squared. You see what's happening? Every single term just kind of scoots over one spot to the right. And doing that sets us up perfectly for the big aha moment. I like to call it the great cancellation. And trust me, it is so satisfying. So let's look at what we've got. We have our original equation on top and the new multiplied one right below it. And notice how we've lined them up. Look closely. Nearly all the terms match up perfectly. The ARs are stacked, the AR squareds are stacked. I think you can see where this is headed. And now for the magic trick. When we subtract that bottom equation from the top one, bam! Everything in the middle, all those terms that lined up perfectly, they just cancel each other out. They completely vanish. And look what we're left with. After all that cancellation, we've got this super simple equation. All that mess in the middle is just gone. All that's left is the very first term from the top equation and the very last term from the bottom one. How cool is that? Okay, from here, it's just a little bit of cleanup with algebra. On the left side, we can factor out the S sub n. On the right, we can factor out the a. Then we just divide both sides to get S sub n all by itself. And there it is. We just built the geometric series formula right from scratch. So that's how it works for a finite number of terms. But what about that original puzzle? The one about the endless, infinite sum? Can we use the same logic for that? The answer is yes, but there is one really important rule, a non-negotiable condition. For an infinite series to actually add up to a real number, the absolute value of that common ratio r has to be less than 1. Think of it like the secret password to get into the finite sum club. So why does that rule matter so much? Well, think about it. If your ratio r is a fraction, let's say 1/2, what happens when you keep multiplying it by itself? 1/2, then a quarter, then an eighth, then a 16th. It gets smaller and smaller, right? So as n, the number of terms, gets infinitely huge, that r to the n part of our formula gets so ridiculously tiny that it's basically 0. Poof! It just vanishes from the equation. And once that r to the n term disappears, our big formula simplifies down to this. It's so elegant. The sum of an infinite series is just a divided by 1 minus r. The first term divided by 1 minus the common ratio. That's it. So simple. Okay, let's put this into practice so you can really see the difference between a series that adds up to a nice, neat answer, we call that converging, and one that just, well, blows up to infinity. So look at these two examples. On the left, our ratio r is 1/2. That's less than 1. So the terms get smaller and smaller, and they're closing in on a final number. That's convergence. But on the right, our ratio is 2. The terms just get bigger and bigger and bigger, shooting off to infinity. That's divergence. And it all comes down to whether r is less than 1. So let's go back to our very first example. 1 plus a half plus a quarter and so on. Okay, so our first term, a, is 1. Our common ratio, r, is 1/2. Let's plug them into our new simple formula. We get 1 divided by 1 minus 1/2. Well, 1 minus a half is just a half. So it's 1 divided by 1/2, which is exactly 2. That whole infinite list of numbers adds up perfectly to 2. So what's the big takeaway here? It's that we didn't just look at a formula and memorize it. We actually took it apart to see how it works. Using that one clever algebra trick, we uncovered the hidden structure that makes this formula so elegant and, more importantly, so reliable. And that kind of leaves us with one final thought. These patterns, they aren't just stuck in math textbooks. You can find them everywhere. I'm talking finance, physics, computer science, even in nature. So the next time you see some pattern where things are shrinking by a constant amount or maybe growing, stop and ask yourself, I wonder if there's a hidden geometric series at play here. Thanks for joining me on this one.